Alright, so in this one we're going to start looking at impulse, momentum, and then talk about center of mass and how center of mass plays a role when we start looking at impulse and momentum of various systems. So impulse and momentum, how we can find the relationship between impulse and momentum, what this really is telling us is how does force and momentum relate to one another. We can start with Newton's laws that force is equal to mass times acceleration. Well, I know that acceleration is really defined as the change in velocity over change in time. And so force is equal to m, change in v over change in t. Well, if I rearrange this a little bit and say F times change in t is equal to m times change in v, we define F times the change in time as the impulse. We define momentum as m times v, so m times change in v is the change in momentum. And so I write out what's called the impulse momentum theorem. A force acting on an object times the time that that force acts on an object is equal to the change in momentum of that object. Now, of course, this particular equation assumes that the forces are constant and that the masses are constant. We'll actually go back when we do a little bit of calculus here in a little bit. We'll look at how this equation actually changes a little bit if, say, maybe force was not constant or mass was changing. Good example of that type of problem is a rocket being launched. Mass is not constant in a rocket, so trying to figure out how the velocity is changing is a little bit more complicated. So another thing that we want to talk about is how do we deal with systems of objects. There are lots of cases when we have two or more objects that collide with one another, or an object that breaks up into multiple objects, and so we want to have a way to deal with complicated systems of objects. So the way we do that is to define what's called the center of mass. And so the center of mass is a point that moves as though all the object or system's mass is located at that point, and all the external forces we can set to act at that location. Really, the way to think of center of mass is if you have a system of objects or some complex object that's weird shaped, where is the average location of mass for that system or that object? This is actually a convenient way to simplify the motion of objects and systems, particularly if that motion is very complex. Say a rotating metal disc, a way to describe that motion, or 3 or 4 objects that are moving in space, maybe the moon orbiting around the Earth, which orbits around the sun. A complex motion of a set of objects that, if we define center of mass to describe that system, it becomes a little bit easier to describe that system. So let's look at ways to find the center of mass. Here's a diagram that comes right out of your textbook, and here I have mass m1 and m2. They're going to use COM as the center of mass. That's what they mean if you ever see me use COM or your textbook use COM. And they're going to say D is the distance between these two objects, and X is the location of the center of mass. One thing to point out about the center of mass is that shifting the axis or shifting the locations of these two objects does not change the position of the center of mass relative to the objects, as long as those two objects stay the same distance apart. So it's true here is the distance between m1 and the center of mass is the same as the distance between m1 and the center of mass there. This is actually pretty convenient because this means that the center of mass can be used to describe both the motion of m1 and m2 together. So the way I would calculate x of the center of mass is to take the mass of object 1 times the position of object 1 and add the mass of object 2 times the position of object 2, and then divide by the mass of the two objects. Basically what this is going to do is say, well, how is the mass and position of object 1 related to one another, mass and position of object 2 related to one another, and what is the mass of the total system. So sometimes use capital M for the mass of the total system. If we had multiple objects, say an infinite number of objects, I would just add mass times position for each object and then divide by the sum of the masses. Now, if you can think of a uniformly distributed mass within an object, you could get a sum of a whole bunch of different objects in there. So another way to write this in summation form is this way: 1 over m times the sum of mass of each little part of that object times its position. We'll also look at this formula a little bit more when we introduce some calculus, because there's another way you can do this for uniformly distributed mass of objects. Now, if we look at in 3 dimensions, we could do the same exercise for y and z and get the same set of three equations. If we defined Ri, what I call the displacement of the center of mass compared to the origin, or the displacement of an object compared to the origin, we can actually define the center of mass this way as well in terms of vector notation. Again, we can do some calculus on these and come up with other ways to work this out later on. So as I say, symmetry can be a very useful shortcut, and we'll actually show that when we deal with uniformly massive objects later on this year. So let's look at problem D1, and in problem D1 we have four particles that are at the corners of a square shown to the right. The sides of the square are each 50 centimeters long, and we want to know relative to the lower left corner of the square, where's the square's center of mass? So really this vector here is what we're looking for. So the first thing I want to do is, this square is a two-dimensional object, so I want to find the x value for the center of mass and the y value for the center of mass. So I'm going to take 1 over the sum of the masses and multiply that by the sum of each mass times its position in the x direction. So we're going to calculate the sum of the masses, 3.5. And I've also defined both the x and the y position. Particle 1 is at 0, 0. Particle 2 on the upper left is at 0, 50. Particle 3 is at 50, 50. And particle 4 is at 50, 0. So if we go and work this out, for the x center of mass, I'd have 0.75 times 0 plus 0.5 times 0 plus 1.25 times 50 plus 1 times 50. For the y thing, I'd have 0.75 times 0 plus 0.5 times 50 plus 1.25 times 50 plus 1 times 0. So if we work those out, we get the position of the center of mass in the x direction is 32.1. What that would suggest to me is that there's more mass on the right-hand side of this square than the left-hand side of this square. And we get a center of mass in the y direction of 25. What that would suggest is that this mass is equally distributed in the top and the bottom of the square. And just looking at the square, we see that that makes sense. So if I wanted to write this out as a vector where the center of mass is located compared to the origin, or the displacement of the center of mass with respect to the origin, I would say 32.1 I hat plus 25 j hat centimeters. So the second problem that I want to do is more of a straight up impulse momentum problem. So I have a 0.75 or 0.7 kilogram ball moving toward a wall at 5 meters per second. The ball hits the wall and strikes and bounces off of it with a speed of 2 meters per second. Tells me how long the ball is in contact with the wall, and I want to know what is the magnitude and direction of the average force the wall applies to the ball. So there we go, my known values. I know the mass, initial and final velocity, and time. I want to find the force. I could say force times change in time, or time is equal to change in momentum. I could say change in momentum is mass times change in velocity. And so the average force should be mass times change in velocity over change in time. So what I would do is calculate that out, plug my numbers in, and I get negative 196 newtons. What that really says is that my vector is, the average force is 196 newtons directed away from the wall. Now another interesting thing that I can do with center of mass is I can do impulse momentum theorem on a more complicated set of objects. In this case, I have 3 objects. I'm going to call them Object 1, Object 2, and Object 3. They're shown in my diagram up on the right. And I have 3 forces, one acting on each of the objects. Their magnitudes are 6, 12, and 14 respectively, and it actually shows how those 4 objects act, or those 4 forces act on the objects. And so what you're looking for is, what is the net force that acts on this system of objects, and also what is the acceleration of that system of objects. So the center of mass of the system will move as if all the mass were there and all the forces were acting there. So I could take force 1 and put it here, force 2 put it there, force 3 that put it there, and add those 3 forces to find the net force on the system. So I'm going to say the net force is equal to mass of the system times acceleration of the center of mass. So what this would really be is F1 plus F2 plus F3 over mass is equal to the acceleration of the center of mass. Now, since these forces are acting in both the x and y direction, I'm going to try to find both the x and y components of that acceleration. So what I need to do first is find, well, the x components of all the forces. Well, F1 and F3 are pretty easy. F1 is in the negative x direction, F3 is in the positive x direction. F2 I want to find the x component of that. And for the y direction, F1 and F3 are pretty easy. They move in the negative and positive x directions. So really all that I need to know is the y component of F2. So if I plug all those in, what I know about the forces and the mass, looks like the total mass should be 16 kilograms, I get those are the two accelerations. Now if I wanted to find the magnitude and direction, I could then draw it out as a right triangle and say the acceleration of the center mass is 1.16 meters per second squared at 27 degrees above the positive x-axis. I could also say the acceleration of the center mass is 1.03 I hat plus 0.53 j hat meters per second squared as well. So that's kind of a quick overview of center of mass and impulse and momentum. We'll start to look at the next set of lessons are collisions and the idea of conservation of momentum.